I'd like to finish this chapter by looking at when our solar system formed. There are a few different ways we can measure the ages of objects in our solar system, but the most accurate one involves radioactive dating of rocks, so that's what we'll look at here. To understand radioactive dating, we need to have another look at the nucleus of an atom. There are two broad categories of nuclear reactions: fission reactions, in which atoms break apart, and fusion reactions, in which they combine together. This is definitely an oversimplification, but it'll give us a picture of what's going on here. If we were studying stars, we would look at fusion, since it's the main power source for stars like the Sun. However, for planets, what we need to look at is fission. Nuclear fission happens when nuclei split apart or spit out material, as shown here. Some atoms do this spontaneously. In fact, as you go to the larger atoms near the bottom of the periodic table, you find that many don't have any stable form. They all split apart on some timescale. Fission is completely random. What this means is that if you have an unstable nucleus, such as a nucleus of uranium, there's no way to predict when it will split apart. It could happen in a few seconds, or it might take a few billion years, and there's no way to tell which it will be. However, if you have 1 trillion uranium atoms, then you can say with considerable accuracy how many of them will decay in any given period of time. You can't say which ones will decay, but you know what fraction will go in a second, or a year, or 1,000,000 years. Companies that sell life insurance do exactly the same kind of calculation. They don't know which of their customers is going to die in any given year, but they know with great accuracy how many customers overall are going to die. If they didn't, they'd go broke. This predictability is what gives us the idea of the half-life. Half-life is the time it takes for 1/2 of any given sample of a radioactive material to decay. For example, the half-life of the most common form of uranium, U-238, is 4.5 billion years. If you wait that long, 1/2 of any given sample of uranium will have broken down into other elements. If you wait 2 half-lives, then only 1/4 of the uranium will be left. After 3 half-lives, it's 1/8, etc. Half-lives can be any length. While some are billions of years, as for uranium, others can be as little as hours, minutes, seconds, or even tiny fractions of a second. Most common rocks have a small amount of radioactive material in them. For example, some forms of potassium are radioactive, and potassium is important in many rocks in the Earth's crust. When potassium-40 decays, it turns into argon-40. But argon is a noble gas, so it doesn't react with other chemical elements. Whenever a rock melts, any argon in it simply escapes away. When that rock solidifies, there's effectively no argon in it. From then on, any argon it has comes from the decay of potassium. So you can put together a graph like this. It shows time on the horizontal axis and the amount of argon-40 and potassium-40 on the vertical. When the rock melts, there's lots of potassium and no argon. After 1.3 billion years, which is 1 half-life of potassium-40, there are equal amounts of potassium-40 and argon-40. After that, there'll be more argon-40 than potassium-40. If the rock melts again, then the argon will escape and the age is reset to 0. Measuring ages this way really measures the time since the rock last melted. There are several types of radioactive decay that are used to measure the ages of rocks, and often scientists use more than one as a cross-check. But they all involve some variation on the process we've looked at here. So what do we find when we measure the ages of rocks? On the Earth, we find rocks of all ages, ranging from newly formed up to 4 billion years old. So we know our planet must be at least this old. Rocks on the Moon are mostly 3 to over 4 billion years old. The oldest rocks from the lunar highlands are around 4.4 billion years old. That pushes the age of our solar system back a little further. However, the oldest rocks we measure are meteorites, samples of material from the asteroid belt. Most meteorites have ages around 4.65 billion years old. Most meteorites appear to have formed as individual grains or small chondrules in space that then accreted together into asteroids without melting. As a result, they probably represent samples of the material the planets form from, and hence they're as old as the solar system as a whole. When uranium decays, it turns into a combination of lead and helium. But if you add up the mass of all of the lead and helium, you'd find that there's a little bit less than the total mass of the uranium you started with. It's not much less, just 1/10% of the starting mass. However, that tiny amount of mass lost is the reason uranium acts as a source of energy. The mass that goes missing is converted directly into energy. As we saw when we were discussing energy a few chapters ago, matter can be converted directly into energy using the relativistic formula E equals mc squared. If you put the mass that disappeared in for m and multiply this by the speed of light squared, you find how much energy is produced. As we saw earlier, even a tiny amount of mass can produce a huge amount of energy. In fact, this sort of fission reaction is the power source for our current nuclear power plants, not to mention the original atomic bomb. In the next chapter, we'll see that it's also the heat source for the interiors of terrestrial planets like the Earth. Okay, now it's time for you to do a simple fission calculation. If 5 kilograms of uranium decays, 1/10% of the mass is converted into energy. So I'd like you to calculate how much energy this produces. Be careful here. Make sure you're putting in the right mass.